So the topic of my presentation is harnessing light for food security. I think it's okay to proceed with. So here is the plan of the presentation. I'll give a brief introduction about the topic, the Raman spectroscopy, the technology. Am I audible?
Yes,
Yes,
Dr.
doctor.
You're
Okay,
audible.
thanks. So the Raman spectroscopy, which is the technology behind it, then of course we are dealing with the food security. So basically, I'm targeting the leafy vegetables. So there are lots of stress which is there in the vegetation uh, during the growing and the cultivation period. So I'll talk about the plant stresses and then how we secure our food with the help of technology. Then I'll conclude my talk. So basically, it's an optical technology, the Raman spectroscopy, which we are using for the food security. So basically, optical technologies are everywhere. If we are talking about the communication, the entertainment, energy, art, manufacturing, security, defense, everywhere. It's almost everywhere. And it grabs the full market in the health sector as well as growing towards the food and agriculture. So basically, one of the application in food and agriculture with the help of optical technology to sustain the demand of the society, we are targeting their stock. So basically, motivated by the food insecurities which are arising from a growing populations as well as climate change, precision agriculture has been proposed as a strategy to increase agriculture productivity. So it will enhance the sustainability, of course. So it requires some new technology which can rapid diagnose the plant stress, any deficiency, or the variable visible or invisible symptoms and subsequent ill loss. So basically, we developed a Raman technology based system, a benchtop system, as well as the portable system with probe, or you can say a clip around the leaf, so which can diagnose any kind of nutrient deficiency or any kind of environmental stress on plant in real time, rapidly, and spectral analysis of plant metabolites. These metabolites are the biomarkers for the plant stress basically. So on that basis, we also developed a spectral library of plant metabolites by which, with the help of that library, a common layman can also explain whether the plant is under any of the disease or any of the stress. So basically, it is a early diagnostic system, so we can save our crop as well as food for the population demand. So, what is Raman spectroscopy? What happened when light fall on a material? So, basically, when light fall on a material, it will simply transmit it. It could be reflected. It could be
Doctor, sorry to
absorbed.
interrupt.
Yep.
I'm still viewing your first slide. Is the
Uh,
slide moving?
yes. Is it okay now?
We are still seeing the first slide.
The first slide.
Yeah.
Oh,
Yeah, now it's moving.
Yeah, it's
okay.
moving, doctor.
So, is it okay now? Can you see the changes in the slide?
Yes, doctor.
The
Okay.
I'm
it's
seeing
on slide 5.
Yeah. So basically, when the light fall on a material, it could be transmitted, reflected, absorbed, and give luminance as well as scattered. So this scattering might be elastic as well as inelastic scattering. And when we are talking about the Raman spectroscopy or the Raman spectrum, so out of this scattering of the light, only 0.0001% light is Raman scattered light. Rest 99.9% is the Rayleigh scattering light, which is of no use for us. So basically, Raman spectroscopy is a spectroscopic technique which is typically used to determine vibrational mode of molecule which provide a chemical fingerprint. So if we want to see the Raman uh, with an unaided eye, so this is what we observe: the full scattering of the light. That blue light is scattered all over. But when we use a filter, so basically this is the Raman scattering, the bands which we want to observe. uh, for designing a system, this is the schematic which we have used for the Raman spectrometer. Of course, we need the three major component: the laser detector as well as the spectrometer. So basically, a monochromatic light source, which is a typical laser, it could be in any of the uh, electromagnetic radiation range. It may be in NIR, it may be UV, it may be visible as per our application, and the filters by which we can remove the extra scattered light which is not shifted, basically not change in color, and detector and spectrometer. So basically, we all know that the plants respond to external stimuli. To protect them from that stressful environment, plant have the ability to control their metabolic activity, and in its process they generate secondary metabolite. So basically, Raman is used to target those secondary metabolites, especially which are a indicator of the plant stress, as we can detect those secondary metabolites in real time with the help of Raman. So they are the they can serve as a rapid diagnostic tool. So in Raman, it measures the molecular vibration in a compound, and its Raman spectrum can act as a fingerprint. It is highly chemical specificity. So this is the one of the main advantage of Raman spectroscopy, that a single spectrum can reveal information about multiple analytes. So here I just show a plant which is under several environmental stresses, like biotic and abiotic stresses. So basically, in abiotic stresses, the plants suffer from heat, drought, cold, salt, saline stress, flood, sometime the metals. So these are responsible for the primary metabolites which plant uptake from the roots, as well as some biotic stress
Sorry to
like.
interrupt you, Dr. Shilpi. We are still in the slide 5. Are you changing the slides?
Yes, I'm continuously changing the slide. Is it okay?
We are still
Can you see the
stuck
slide?
on slide 5. No, now it's changing. Yeah.
uh, is it okay if I start with
Yeah.
this without presentation mode? Is this okay? Or
Yeah. Without presentation mode, I guess it's okay.
okay, if it's stuck, please let me know so that I just change it. So there are several biotic stress as well: the pathogen, the insect, the herbicides, all the phytohormones are generate for the plant defense when it is under biotic stress. So basically, under these abiotic stress, plant develop the metabolites, the primary and the secondary metabolites, which comes in front for the response, or it shows some deficiency. And wherever there is a biotic stress, the phytohormones basically abbreviated in the plant in response to that stimuli. So here I'm just
You are in
showing the.
presentation mode, I guess. We are still stuck on slide 9. Yeah, now
Is
it's
it okay?
visible. Yeah.
Okay. So if we talk about all these abiotic stress, I'm showing the Raman spectra from the two abiotic stress, the nutrient deficiency as well as the light deficiency. So if we're talking about the nutrient deficiency, so it may be all the three major nutrients which plant uptake, like nitrogen, phosphorus, and potassium. So basically, here I'm showing the nitrogen. This is the first time with the MIT and the DISTAP Singapore we developed this Raman peak, the nitrate Raman peak, during the nutrient stress in the plant. And in this Raman spectra, when we took the three biological replicate, one in the case of nutrient deficiency, the nitrogen deficiency, and the other three biological replicate with in normal condition or actual the model plants. What we observe during the processing, we see a major change in this peak, which is closely related to 1047, and this peak we identify as a nitrate peak. So this nutrient deficiency, this nitrogen deficiency in plant in the leafy vegetable, we observe within 1.5 day, or you can say in within 24 hours, you can observe this deficiency. Normally, our farmers or the person, the grower, will identify it when we observe the change in the color of the leaf. Either it is slightly yellow or towards the brown color, then only we can identify this nutrient deficiency, and by that time the whole crop or the plant is like destroy. That's why this early diagnosis of nutrient deficiency is needed, and it is fulfilled with the help of Raman spectroscopy. In a second spectra, I have shown the light stress on the plant. Of course, in cities or the places like where there is no field where we can grow the plant, we normally grow the plant in the urban farm environment, in a closed environment. So basically we fulfill the need of light with the help of LEDs or different color LEDs. So these LEDs is also having a kind of stress because there is a limited space uh, for a plant. So basically that plant is under three type of light stress. So basically one is white light, which is continuously supplied when the plant is in urban farm. Then there is a moderate shade. That moderate shade plant is getting because of its neighboring plant. And of course the next is the deep shade condition, where there is a dark or the plant is below the neighboring plant, so there is no light is reaching to the plant. So in all the scenarios, there the uh, nutrients and the capabilities of plant are suffer. So basically we observe the carotenoid, which is the major metabolites, and we can get it only by the plants, and the fruits is suffer. So this basically these two peaks are for the carotenoids. So with respect to the plants, we are observing the change in these carotenoids peak under different light stress condition. So this is how the Raman spectroscopy can tell whether the plant is under stress or not, which metabolites is coming up or showing change with respect to which type of abiotic or the biotic stress. So here I'm just showing the three Raman system which we have developed in Desktop, a lab under the SMART with the MIT professors or the MIT team. So we developed a portable Raman system which is showing here, and we developed this interface by which we can simply clip the leaf in urban farm in this leaf probe sensor, and then observe the Raman spectrometer. So within 5 uh, or 10 second, it will tell you whether the plant is under any of the stress. So on the right side I am showing the benchtop systems. So this is basically the standard endorsed system which most of the lab are having. So these two system also confirm the capability of the portable system what we have developed for the plant stress. So here I'm just showing like how we develop this system, what are the capabilities of this system, how we design this leaf clip sensor, and on the right side, top right side, we are just obtaining the spectra from the leafy vegetables. So here this is the pok choy and choysum, and on the below tray there are lettuce, which we are observing whether they are under any kind of stress. So all these vegetables were grown in the hydroponic medium. We verify the portable Raman system. So here I'm just testing the portable Raman system, this type of spectrum, Raman spectrum I'm observing. And this is under the benchtop system. I just cut the leaf and using it under the microscope and observing the Raman spectrum. We have acquired the Raman spectra of all the leafy vegetables and identify the major peaks with respect to the lignin, pectin, cellulose, phenylalanine, all the primary and the secondary metabolites, which we can observe the change under the stress condition. For the further systematic way, or for a layman person, we did the mathematical multivariate analysis for understanding these biotic and abiotic stress. So we took help from the principal component analysis, and of course the AI to develop the system so that anybody can understand what is the results. So basically these are the Raman spectra under different type of stress, and when we observe the PCA we can see that the control plant as well as bacterial infected plant are showing the far separate apart spectra, by which we can identify whether the plant is healthy or it is under any kind of stress. So this result is only after 48 hours of the infection. Basically we need 4 to 5 days to observe the change for the biotic stress. For the shade also we did the principal component analysis and can simply observe that under different kind of stress like moderate shade, deep shade and the white light shade, the plant carotenoid peak is showing a significant change. These are the results for the nutrient stress. For the nitrogen deficiency, what I just showed, this 1047 is a peak with respect to the nitrogen stress, and we can simply identify with the help of principal component analysis whether the plant is under nutrient stress or not. So here is the biotic stress. The xanthomonas infection is there in the plant, and when we observe we can simply show that two healthy plant as well as the infected plant, the control and the infected, are separated with the help of multivariate analysis. We also try to obtain the VOCs, the volatile organic compound, with the help of this portable Raman system, because in the cosmetic perfumery industry as well as in the healthcare also, these essential oil from the plants and the spices are needed. Like from the pepper we need pepperine, and eugenol, a different type of fragrance, that volatile organic compound we can also identify with the help of these portable Raman system. So here is the spectra which is I'm showing from a basil trichome. So this is the spectra. We confirm the presence of eugenol here as well in mint. So with the Raman spectra we can simply identify which plant is better for producing more VOCs or like further essential oil. So this is the study, the novel photonic Raman sensor. It enables detection of plant stress and the study of production of plant secondary metabolites in real time. It is also has the potential to transform agriculture, discover plant biosynthesis pathway, and revolutionize urban farming. Thank you. Question, please.